In Chapter 3, we're going to start talking about relations and functions. Section 3.1 deals with graphing basic relationships. There are 4 very simple, quick warm-up problems that ask you to state whether each word or phrase represents an amount that is increasing, decreasing, or constant. So please complete those 4 warm-up problems. All right, so let's check out our answers. For number 1, stays the same would mean to remain constant, not changing. Number 2, rising would mean to increase. 3, dropping would be to decrease. And 4, slowing down would mean to decrease. So our goals for today are to match simple graphs with situations and to make a general graph of a relationship. So there's 2 very important vocabulary words that you need to know basically from here on. Those words are continuous graph versus discrete graph. Now, a continuous graph is a graph that is connected. It's a connected line or curve. Whereas a discrete graph consists of only distinct points. They are individual points. Okay, so continuous graph, continuous is connected. Discrete is distinct points, which are not connected. Okay, so in this lesson, we're going to kind of distinguish between these situations where we will have a continuous relationship, which would mean that we would connect our line or curve, versus our discrete situations where we have distinct individual, not connected points. So we can use graphs to illustrate many different situations. For example, trends shown on a cardiograph can help a doctor to see how a patient's heart is functioning. So in order to relate a graph to a given situation, we need to use keywords in the description. We have to make sure that we pay very, very close attention to our axes labels, meaning the labels on our x-axis, the horizontal axis, and the y-axis. So we're going to jump straight into example 1 that says, each day several leaves fall from a tree. One day a gust of wind blows off many leaves. Eventually there are no more leaves on the tree. Choose the graph that best represents the situation. Okay, so each day several leaves fall from the tree. One day a gust of wind blows off many leaves, so a lot of leaves fall off. Eventually there are no more leaves on the tree. Okay, so we've got 3 different pieces here. So which one of these graphs would best represent the situation? So we're starting off stating that several leaves fall from a tree, but then there's a gust of wind that blows a whole lot off. Okay, so graph A is going against that first part. Okay, it says several leaves fall from a tree. So graph A, if we look at our time versus our leaves, graph A is showing that the leaves are increasing initially. So graph A is wrong. Graph B is decreasing to start, as is graph C. Okay, so B and C are both in play after this first piece that says several leaves fall from a tree. Now the second piece, it says that the gust of wind blows off many leaves. So there's a whole lot of leaves that are falling off at once. So let's kind of say, okay, the highlighted part here in yellow matches and corresponds to the yellow statement. Now for the next piece, graph B, notice that it's more severely going downward. Whereas for graph C, it flattens out for the second segment, which would mean that the leaves would be staying constant. Okay, and our second segment, we need many leaves to blow off the tree, so more than blew off initially. Okay, so far, I mean, A and C are both crossed off, so B is going to be our answer, and let's verify that then with the last piece that says eventually there are no more leaves on the tree. Well, that means that the leaves continue to come off and the leaves are now down to 0. Okay, so graph B is definitely our answer there. In number 2, the air temperature increased steadily for several hours and then remained constant. At the end of the day, the temperature increased slightly before dropping sharply. So using these clues and the descriptors, decide whether graph A, B, or C represents this situation. All right, so hopefully for number 2, you selected graph C. Okay, time is our x-axis. The y-axis is our temperature. So it's saying the temperature increased steadily for several hours, then remained constant, which is the green piece. The temperature increased slightly before dropping sharply. Okay, so graph C definitely represents that information. So examples 1 and 2 were both continuous graphs because time is continuous and these situations continue flowing. Okay, it's not like we have things with specific numbers of people or numbers of objects that we must always stick with whole numbers, which would be a discrete graph. Okay, so these were connected lines or curves and they were continuous. The distinct point graphs are going to be discretes. Okay, so notice these curves were connected. This theme park attendance graph is individual points. Okay, so these are continuous graphs. Okay, because they are connected. Whereas before we even talk about what's happening here in this next part, this is a discrete graph. Okay, because that's a series of distinct points that are not being connected. Okay, so the graph of theme park attendance is an example of a discrete graph. It consists of distinct points because each year is distinct and people are counted only in whole numbers. The values between whole numbers are not included since they have no meaning for the situation. Okay. So let's take a look at number 3. It says a truck driver enters a street, drives at a constant speed, stops at a light, and then continues. Now, most often when you enter a street, you're not kind of entering at that constant steady speed. You're kind of picking up some pace. So if we're talking about entering a street, he has some speed, but he's going to be increasing as he goes farther onto the street. So that's going to be my first little piece. Then if he drives at a constant speed, his speed is remaining the same, so we've got a flat line. And he's going to stop at a light. Well, his speed, which is our y-axis label, okay, needs to go down to 0. Well, it would be not very realistic to just draw a straight vertical line because you're not going to go from, say, 40 miles an hour to 0 miles an hour at the drop of a dime or hat or whatever the phrase may be. So let me undo that line. So we've got to slow down to eventually come to a stop. And then he's going to continue on. So then his speed is going to gradually start up again. Okay, so entering a street, you generally start off a little slower, then you start to pick up speed. Then you drive at a constant speed. Then we stop at a light. Well, it takes time to go from that certain speed to a speed of 0, and then continuing on. Okay. So these axes labels are really important. Okay, so this would be a continuous situation, okay, because time itself is continuous, okay, and the speed with respect to time is going to remain continuous. So this was a continuous graph. It's connected. Let's take a look at number 4. A small bookstore sold between 5 and 8 books each day for 7 days. Okay, so let's plot these ordered pairs. So I'd like you to just take a minute and plot each of these ordered pairs. X represents the day number, whereas Y represents the number of books sold. So go ahead and plot those points. Okay, so here's what our graph should look like. Now the question is, would this be a continuous graph? Should we connect the points? Well, this is actually similar to our theme park attendance, where the years are distinct and numbers of people. It's always going to be a whole number. This is going to be the same situation. Days are distinct as our number of books sold. So this particular situation will remain a discrete, non-connected graph. Okay, representing the relationship between day number, and quantity of books sold for those 7 days. Number 5 says Jamie is taking an 8-week keyboarding class. At the end of each week, she takes a test to find the number of words she can type per minute. She improves each week. So I want you to plot these ordered pairs where X represents the week number and Y is our words per minute, and decide whether this is a discrete or continuous situation. Okay, would test scores be discrete or continuous? In looking at number 5, we've got a nice little pattern. We've got a trend. Jamie's speed is definitely improving each week, but this would also be a discrete graph because there's no logic that would connect the individual test scores, because she's taking a time typing test over 8 weeks, and those are distinct, separate assessments. Okay, so this will be a discrete graph. We will not connect those dots. What about 6? Henry begins to drain a water tank by opening a valve. So he's starting to drain a tank by opening a valve. Then he opens another valve. Then he closes the first valve. Well, what would that mean? Think about that. He then leaves the second valve open until the tank is empty. Okay, so if we look at our X and Y axes labels, X is time, and 99.9% of the time, the X axis for a graph will represent time. The Y axis represents water level. And we're talking about the water level in a water tank. So the tank is full. So he starts to begin draining the water by opening up one valve. Okay, so he opens up a valve and water is draining out. It's hard to draw straight lines here. So water is coming out of the tank. But then once he opens up another valve, the water is coming out of the tank faster. So that downward line needs to now become more severe. Okay. But then if he closes the first valve, he now only has one valve open again. So now the water is continuing to drain, but not as fast. So it's not going to be as steep of a line. And then he leaves the second valve open until the tank is empty. So because he closed the first valve and he leaves that open, we're going to just kind of continue that line at the same rate until we meet that x-axis, which would mean that the water level is now at 0, empty. So the green and pink colors are actually they're the same, they're a continuation, because when he closes that first valve, it's now only at the second valve being open, and it remains open until it's empty. So these two continuing just are going to remain at that same rate, declining, but not quite as fast as when both valves were open. Okay, notice how steep this one is. Okay, so both valves open. Okay, so we want to definitely make sure we read those axes labels. Okay, so next we've got both graphs show a relationship about a child going down a slide. Okay, so take a look at X and Y. X is time. Y is distance from the ground in graph A, but speed in graph B. Okay, so graph A represents the child's distance from the ground related to time. So he's starting up at the top, going down, 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 and then this is kind of like that flat part. And when you get off a slide, like you're not usually literally on the ground. Okay, so that's why it just kind of levels out here at the very end. Okay, for graph A. Graph B represents something completely different. It's the child's speed related to time. Okay, so you're starting off, when you first get on that slide, you're not moving at all. And then your speed starts to increase. Okay, you're going pretty fast, and then eventually you reach your max speed, and then towards the end, you eventually slow down until you're at the very, very bottom. Okay, so you've got to make sure that we always pay attention to our axes labels. Super duper important. All right, so now we've got two more problems, and this is actually the reverse of what we did initially. It says write a situation to represent each graph. Okay, so here notice it's speed with respect to time. Okay, so we're traveling at a pretty high speed, slowing down, then we're traveling at a constant rate of speed for a period of time, and then slowing down to a speed of 0, coming to a stop. In number 8, we've got a discrete graph. So 7 was continuous, 8 is discrete. And notice we've got numbers of students on the x-axis, pizzas bought on the y-axis, because you can only buy whole numbers of pizzas. And based on the number of students you have, sometimes you're going to reach a point where it's like, okay, one pizza is not going to be enough. So now I need to order a whole second pizza, even though it's going to be too much, but one's not enough. Okay, so think about and give me a situation for either 7 or 8. Okay, and I talked about them, but I want a real life situation to represent the graph. All right, so how do your scenarios compare? Number 7 for the continuous graph with the speed declining, remaining constant, and then going down to 0. I came up with a scenario that after seeing a police officer on the highway, Sean slows down and then puts his car in cruise control at 65 miles per hour, which is the speed limit. Okay, so he was going at a certain rate, but then he slowed down, put his car on cruise control, and is now remaining at a constant speed of 65 miles an hour. However, unfortunately, the police officer clocked Sean going 83 miles per hour and pulled him over to give him a ticket. So Sean went from going a steady 65 miles per hour to decreasing his speed and coming to a complete stop. And then number 8, okay, about our pizzas bought versus number of students. So a pizza party for up to 4 students requires 1 pizza, while 2 pizzas would be needed if there are 5 to 8 students. The number of pizzas ordered depends on the number of students. Okay, and if there would be a 9th student, well, we would probably need a whole nother pizza because, well, it looks like we can have 1 pizza for every 4 students. Okay, so once we exceed 4 or any multiple of 4, we need to add in an additional pizza. And this is a discrete graph because the number of students will be whole numbers, in addition to the number of pizzas purchased will also remain whole numbers.